the area of a velocity time graph. But before we do that, let's recap the area of a speed time graph. The area of a speed time graph is actually equal to the distance gone by the object. All we had to do was work out the area of a speed time graph, divide it up into triangles and rectangles, and the total area of it was equal to the distance gone. Speed is a scalar quantity, and so is distance, and they don't need direction to fully describe them. But a velocity time graph is different because it shows velocity, which is a vector quantity, and that needs size and direction. Now, we got over this by drawing on the graph the positive values of velocity to indicate that the object is moving to the right, and negative values of velocity to indicate that the object is moving to the left. Now, the area of a velocity time graph is going to be equal to the object's displacement, its final displacement. So displacement is a vector quantity that needs a magnitude and direction as well. So this is where we have to be very careful here, because the area above the time axis, which involves the positive velocities, then that's going to indicate the displacement to the right. And the area below the time axis, which involves the negative velocities, is going to indicate or represent the displacement to the left. So we can work out the displacement to the right, and we can work out the displacement to the left. So let's try the graph out and see if we can match up what's happening with this little car as it moves along this road. And we're taking the start of the car from its bumper, which is at 0 meters. So let's set the car off in motion and see the velocity time graph it produces. The car's accelerating, it's going at constant speed, decelerating to a stop, and its displacement is 20 meters to the right. It has a moment to stop, and then it reverses back the way, and you can see its final displacement is going to be 10 meters to the right. So the final displacement of that car is going to be 10 meters to the right, and that's the vector representing the displacement of the car, the final displacement of the car. Now, let's look at the areas above the time axis, because that's going to give us the displacement to the right. And if we work that out and look at it, split it up into different parts, if we work it out, we get a total of 20 meters. And that's true, the car did start at 0, and it did end up 20 meters away from its start. So in the first part of its journey, we could represent the vector as the following. Displacement vector would be 20 meters to the right. Now in the second part of the journey, after its initial little stop, it went back the way, and its displacement back the way was 10 meters. We work out that area. So the vector representing that would be 10 meters back the way. So here we have the top area, which represents displacement going forward to the right, 20 meters to the right, followed by 10 meters back to the left. So the resultant displacement of that car is going to be 10 meters to the right, which is what we've got up here. So to find the resultant displacement of a car or an object from a velocity time graph, we've just got to look at the areas of the graph and have the top area representing the object to the right and the bottom area representing the object to the left. And as a rule of thumb, we just take the positive and take away the bottom area. So we'll have 20, take away 10, which is going to give us a resultant displacement of 10 meters to the right. Here's a computer simulation of a ball being thrown into the air from the ground. The white arrow represents the ball's initial velocity vector, and you can see it's pointing upwards. The green bar represents the ground. On the right hand side of your screen, you'll be seeing a velocity time graph drawn of that motion in real time. So let's throw the ball into the air with that initial velocity and find out what the initial velocity was and the shape of the velocity time graph. The ball is now landed, and we can see that we've got the velocity time graph on our right. Now we're going to analyse that velocity time graph and see what it's going to tell us. First thing we notice about the velocity time graph of the ball thrown into the air is at time t equal to 0, at the moment it left the ground, it had an upward velocity of 20 metres per second. Then after 2 seconds we can see that its velocity has been reduced to 0 metres per second, which means the ball has actually stopped. After the 2 second mark, we can see that the ball's velocity is increasing in the negative direction because the velocities are increasing in the negative numbers, and it finally lands at 4 seconds into the flight with a velocity of minus 20 metres per second, which means 20 metres per second downwards. So that ball was decelerated on the way up and accelerated on the way down. And because it's just one slope of the graph, it means that the acceleration was only one kind, and that was acting downwards all the time. And we can guess what that acceleration was. It was acceleration due to the force of gravity. Now, by analysing the area under the graph, I can work out the displacement of the ball. Remember, the area of a velocity time graph is displacement, and displacement has size and direction. So that top triangle I can shade in a blue colour, I can work out its area, and I know that the value of it will be the displacement upwards of the ball. So the triangle has got a breadth of a base of 2 units and a height of 20. So the area of that triangle is going to be 1/2 times the base times the height, which equals 1/2 times the base, which is 2, times the height, which is 20. So that's going to give us a number of 20, which corresponds to a displacement upwards of 20 metres. So I now know that that ball was displaced upwards by 20 metres, and I can draw its displacement vector from the ground like that, and I know its value is going to be 20 metres upwards. Now, I think you can guess what the area of the bottom triangle is. It must be 20 metres, and the displacement vector must be pointing downwards because the ball came back to its original position. So let's work it out anyway. We'll shade in that part of the graph with a green colour, and we'll work out the area of that graph. The area of the graph is similarly going to be area is going to be equal to 1/2 base times the height. And the base of the triangle is still going to be, in this case, 2. You're going from 2 to 4, so it's going to be 2. 1/2 times 2. And the height of it is going to be 20. Oops, put multiplying sign in there. So it's going to be 20 for the number. The area is going to be 20, which corresponds to the displacement downwards to be 20 metres. And I can draw that in a vector, same colour. There's the displacement vector downwards from the top, and you can see that that's going to have a value of 20 metres downwards. So these two vectors are going to cancel each other out. 20 metres upwards displacement followed by a 20 metres downward displacement gives you the resultant displacement equal to 0. So resultant displacement would be equal to 0, and we see that from the simulation because the ball arrives back from where it started off from. And looking at the velocity time graph, we can see the top area, which represents the displacement upwards, is going to be cancelled out by the bottom area, which represents the displacement downwards.